This is an attempt to show that the Monty Hall problem is a simple case of selection bias. The key is to show that when the problem is viewed symmetrically, there is no paradox. A general formula will be calculated for the symmetrical case with a variable number of doors containing goats and cars. Also, the host can remove any type of door and any number of doors. The player will still never have the option to select an open door. The case where the host is untrustworthy will also be explored, and a general formula will be calculated here as well. At the end, we will see why Monty Hall is dependent on a selection from the host, and why it will not matter whether the players switch or not when doors are opened due to a random process. But first, let's look at an example. Imagine you are at a tombola at the fair. After you have drawn a lot, most of the blanks are discarded. There are still the same number of winning tickets left in the bowl, as they are put back in the bowl if selected. In this case, most people would like to swap the first ticket for a new one, as the fraction of winning tickets is now bigger. Vice versa, if most of the winning tickets were picked out and discarded, it would not be beneficial to swap the current ticket for a new ticket, as there is now a smaller fraction of winning tickets in the bowl. A general formula. We allow the host to open doors containing both cars and goats. The player is never allowed to choose an open door. This makes the solution more general and symmetrical. If you somehow do not like the idea of the host showing a car, the constant m can just be ignored. The total number of doors will be denoted uppercase D. The total number of cars will be denoted uppercase C. Lowercase m denotes the number of cars shown. Lowercase n denotes the number of goats shown. First, we divide the problem in two cases: when the player unknowingly has picked a car, and when the player unknowingly has picked a goat. The fraction of time when a car is picked equals the number of cars divided by the total number of doors. And the fraction of time when a goat is picked is the number of goats divided by the total number of doors. The number of goats in the enumerator is equal to the total number of doors minus the number of cars. Now we calculate the winning chance in the two cases when the player chooses to switch doors. When a car is picked, the enumerator is the number of cars left behind the remaining doors, from which the player can choose. This is the total number of cars, minus the doors opened by the host showing cars, and minus the car which the player unknowingly picked in the first place. The denominator is the number of doors left to choose from. This is the total number of doors minus the open doors with cars and goats, and minus the first door chosen. In a similar way, we calculate the case where a goat is picked, and the player chooses to switch doors. The enumerator is the total number of cars left. In this case, it is the total number of cars minus the cars being shown, but not minus 1 as the first door was a goat. The number of doors left is the same as before. The total number of doors minus the open doors in the first door which are out. Now we just need to make a weighted average for the two cases, and we get the final formula for winning Monty Hall when switching doors. We can simplify the expression, as we have a common denominator. And here we have it, the general formula for Monty Hall when switching. In the second half of this video, we will look at the case where the host helps and counteracts the player at some given rate. A general formula will be calculated, describing the equilibrium point, given this ratio and the variables used in the first half. We will also examine the case of doors being opened and discarded due to a random process. Here, switching will never change the winning chances. This can be shown mathematically. But there is also a powerful and simple way to show this using logic alone. If you want to play with Monty Hall yourself, there is a link in the description below. Also, there is a link to some simple Java code. With this, you can simulate and compare the results to the predictions of the equations in this video. Have fun!